warm welcome to one and all present here on the third day of this 1 week ATAL sponsored faculty development program on green technology for sustainable life Indian perspective. We are blessed to have with us Dr. Rakesh Maurya as today's resource person. I would like to request co-coordinator Dr. Nirav Rai to please welcome him with the sapling. So I take pleasure in introducing our today's resource person, Dr. Rakesh Maurya. Dr. Rakesh Maurya is from Department of Electrical Engineering, Sardar Vallabhbhai National Institute of Technology, Surat. During his quite successful and rich academic and research journey till date, Sir has published in excess of 60 research articles in many reputed national international journals and conference proceedings. He has been a guide of 10 PhD scholars. Sir has also received many prestigious national international awards, and he has reviewed many prestigious conferences and journals. He has been invited to deliver expert lectures on many prestigious academic platforms. So during his last 18 years of quite rich academic journey, he has been bestowed with many accolades. So we are blessed to have with us you, sir, today. We are looking forward to hear from you during the 2 sessions today. Over to you, sir.
Hello. Am I audible?
Yes, sir.
Yes, sir. Very good morning to all of you. My lecture is focused on 2 parts. One is a very general introduction, and the second is more specific about my research. I hope I am audible from here also. Yes? Okay. So let me start with the first. What is electric vehicle and what is the future of electric vehicle? Okay. The main idea of putting this content is one side. Yes, now. So the main idea is to know what is the specifications required for electric vehicle and how you can develop charger for electric vehicle. So the first part of my discussion will be the electric vehicle in general, their specifications, and then we will be focused on what is the size of the battery, what is the size of the charger, and how best you can improve the charger, how best you can reduce the infrastructure, because government cannot reach to each individual for the charging. But we can, as an engineer, as a developer, we can make the system so that it can reach to, it can be featured in the vehicle itself so that you can charge wherever you want. Okay, only the source should be there. That is the case. So, basically my area of research is I have improved power converters for electric vehicle charging system. This is one of the area. Second is the multi-phase induction motor drive. I have few 2 to 3 year work with multi-phase induction motor drive. I am also working with the distributed generation system and their integration with DC grid, DC microgrid, as well as the DC AC grid. And lastly, custom power devices. Myself along with my colleague, I am working with the area of power quality improvement in the power system network. Okay. So now coming to this particular part. So first I will start with the electric vehicle as a state of art, then the type of vehicles, then the type of motor and converter used for charging, and lastly the research highlight which I have carried out in last 5 to 10 years that I will be going to put up here. Okay. Now the first question comes, why so much interest in electric vehicle in today's? The first is even though this data is very old, but I tried to search and Google studied what is the top 20 cities in our country, in the world, top 20 cities which is most polluted in the world. And you will be surprised to know out of 20, 14 is from our country. So it's a very alarming for us in terms of the air quality index of the cities. Most of the urban cities, they are highly polluted and the people feel uncomfort in living. Now second is regarding the import of oil, petroleum goods from other places, other foreign countries. From 1981 till 2015, even if you prolong till 22, I have searched the data, and it was more than 40 times higher we are consuming petroleum products. So one time it shows the growth of the country because we are consuming more and more oil, more and more petroleum goods in order to live the good life. But anyhow, we are dependent on the other places where they are rich in their petroleum products. So we should make an alternate solution where we are rich in that local solution, local sources. Okay, so that we need to think of. And the third part, if you see the efficiency, normally the IC engine based vehicle is having efficiency 32 means at the most 20% or 30%. Whereas if you go electric vehicle, you will find most of our machine is over 90-80% efficient. And if you use the concept of energy sources, means optimal operation of the system, it will be as high as 90%. So the efficiency of electrical vehicle, electric motor-based system is highly efficient as compared to IC engine-based vehicle. So these are the three aspects which forces people to think of alternate means of transportation than the conventional. Okay. Now second thing about the world, in total the world, this shows the production of oil, the blue shows the world oil production, and second shows the consumption demand. And as the year progresses, the gap between the consumption and production increases. So we need to fulfill that gap with the help of some other source of energy. Otherwise, we have to make some alternative so that optimal break-even should be whatever energy we are producing, the same should be consumed. Okay, but here the demand is more and consumption production is less. So obviously the cost and other things will go high. This part I have already. This is also one of the aspects. If you see the most of our temperature, Earth temperature, it keep on increasing year by year. From 1888 till 2020, the temperature is keep on increasing. Though it's increasing with a decade of 5 years average it has been taken, and it is so that it keep on increasing, and that will lead to other aspect of sources like the temperature will rise, glacier will melt, and the living surrounding the coastal area will be affected. Okay, so that all also forces us to look for how do you curtail the rise of temperature. Even the world level summits has been organized, and people have worry about how to curtail the rise of the earth temperature. And now, if you see the variety of vehicle, from the two-wheeler till four-wheeler and even electric bus, and these all are this variety of vehicles are available, and they are operated through either fully battery operated or semi or hybrid mode. So these vehicles are available. So that is why the people have a interest of that. They have a variety of option. And so some of the global context, the one is the climate change, then advances in renewable energies. Because earlier we have only the power grid as a network, and we are used to take power from the grid only. But due to renewable sources, and we are going towards the clean energy, as our topic of your FDP is more focused towards the green energy, sustainable energy. So we need to focus more about the renewable cases. So due to advent of power electronics, due to development of power electronics, now the people have choice, many choices. Whatever energy available, we can convert them in the form required or compatible for our system. So that can be possible through the green renewable sources. You can interface, and we have a very good number of technology available where you can use, and it is frequently available. You need not to search. 20 to 30 years before, people have no option. They used to take power only from the grid, but now the scenario has been changed. So this is one aspect, and the benefit of electric vehicle is almost in operational case, no fuel is required. When operating, no emission is there. Instant torque, I will show. Within a fraction of second, you can accelerate your car at a very high speed, and that is possible. And some of the model, it is like Tesla model, it reached to 60 miles per hour in 2.5 seconds. Such a acceleration. See, 60 in 8 seconds, Nissan Leaf. Okay, so some of the like cheaper to maintain, health benefits, safety improvement, these are energy security. As I said, we are mostly depends on the petroleum product to operate the IC engine based vehicle, and which we are borrowing from the other places. But if you are producing the source of energy locally, we will be sustainable, we will be self-dependent on our sources. So that can be, energy security can be issued, reduced. Now coming to the vehicle, normally 3 types of vehicles are available. One is the battery operated vehicle. Hello. So battery operated vehicle means, a very simple, we have a battery, we have an energy source as a battery, then there is a power converter, and then there is a converter, and then it is motor. And motor is connected with the transmission system, and it is going to the, let's see if that will be easy to understand. Here, see, if I call about the battery operated vehicle, means we have a transmission system which is coupled with the vehicle wheel. Then battery is the source of energy, motor, and here motor is the driving. In between battery and motor there is a power converter. It's a very general basic diagram. So here we have only source of energy as a battery, and battery is powering to the machine, and it is driving. So the one class of EV is the battery operated EV. Then second is the, let's say, coming to the plug-in electric vehicle. Plug-in electric vehicle means you can think of this particular configuration here, hybrid electric vehicle, where they are designed in such a manner where even if you see the plug-in electric vehicle and a battery operated vehicle. So battery operated vehicle is, you can assume there is a battery, it provides energy to motor and it is driving. But you can charge the battery whenever required at the dedicated place, or you have to stop and you have to charge. Okay. Plug-in, there is a facility you can plug in wherever you want. Means charger is inbuilt in the vehicle itself and you can charge it. So that is comes under the plug-in electric vehicle. Okay. Hybrid vehicle is the one. Hybrid vehicle means you have a vehicle along with the IC engine based system, and the charging you cannot charge the battery separately. Whenever the IC engine is running, during the operation, suppose some brakes are applied or the conditions are there where the power is retrieved from the rotational energy back to the battery. During that process you can charge. And if your vehicle is running on the road and it is moving, suppose if it is running on the road and in between after some times your battery will start powering your whole system and it will drive. Like some of the car feature is a hybrid vehicle in which after some times your operation will shift to the battery and battery will start providing energy to load. But you cannot have a feature to charge it on the vehicle, on the grid. Through the grid you cannot charge it. It is alone only the hybrid and it is charging during the operation through the engine when the fuel based system is operating. So that is one. And this is a conventional petroleum IC engine based vehicle. So I hope in these three parts I have covered: battery operated, plug-in, and then the hybrid. Hybrid means you need not to have a charging facility separately. During operation, while applying brake, while running smooth running, you can charge your electric vehicle. Now let us come to some of the model, because the purpose of depicting this model is to know what is the power level, what is the current. So let's see this particular. We have a BES, battery operated vehicle, in which the battery rating is of 95 kilowatt hours and the voltage is 396. If you have a four-wheeler vehicle, then a type of the battery is the lithium-ion battery which is being used for this case. Okay, see the performance parameter. Within 6.6 seconds, your vehicle accelerate up to 100 km per hour. So that is the acceleration time. And top speed you can achieve is 200 km per hour. Maximum, see here we have a front wheel, front motor, rear motor, front torque, rear torque, and the combination. Since we have a four wheel, so the front wheel is driven by the front motor, this front motor, and its capacity is around 125 kilowatt. Similarly, the back side also we have a rear motor which is coupled with through transmission system to the back side of the wheel. So that is the rear motor, it is a 140 kilowatt. And in combination, you can provide power up to 265. Okay, the whole system can be driven, both motor can be operated simultaneously to provide this much power. Similarly, the torque level is also mentioned. And this is called all-wheel drive system. All-wheel drive system because here we have two motors, front wheel and back. Okay, but there are configurations where each wheel is operated independently. And in that case, that is called the hub motor or in wheel motor, where in wheel motor is attached and there are such four motors connected to that part. I will show the configuration. But that is, you can think of it is an all-wheel motor. Efficiency in terms of, so these are the performance parameters, these are the type of the machine we have. Now let's see some of more model. See here, acceleration time within 6, it can reach 80 km per hour. Top speed 128. Speed range, this electric range, in one charge it can move up to 112 km per hour. This is the maximum power, and this is the front wheel. You have only one wheel drive system. In front, the motor is connected and it is driving the entire car. See, this is the battery operated. Now the battery, fully battery operated. The speed is, acceleration time is 14 seconds. It reached 200 km. Top speed, and then four-wheel drive. So these are the requirements. This is another motor, another vehicle. See some more model like. So if you see in entire case, I will stop wherever it is required. But you can see the battery operated only, where within 20 seconds it can reach up 100. So such a good acceleration. Speed range. This range is also up to 100 kilometers range. All-wheel drive system. See the Mahindra. The technology used, battery technology, is the EV. Here, battery operated lithium-ion battery, and the acceleration time within 9 seconds it can reach up to 96 km per hour. Top speed, and these all. Okay, so our main concern is you must know the power level of the motor which is used to drive the system. If you see here, the maximum power the motor can operate is 67 kilowatt. So you can see if the motor is designed with 67 kilowatt power, so what should be the winding current? So that means the motor can withstand the current corresponding to 67 kV. Okay, I will come to that part later on. And here rear wheel drive system is the motor and the converter all are connected to drive the back side of the motor, back side of the wheel. So that part is there. Now see some of the example of plug-in electric vehicle. Plug-in electric vehicle, as I said, it is operated with fuel also. It is operated with battery also, and some of the feature, the fuel-based system is not available. This battery can be charged, means charger is placed within the battery, within the car itself. It is designed by the manufacturer of the car, and you can only plug in wherever you want. That is plug-in. Okay, in battery operated, once the battery is charged, you need, there is no feature of charging the battery within the vehicle. When the battery is fully drained or partially drained, you stop the car, you use the charger, either off-board charger or dedicated charger, and you can charge it. But here the charger is placed within the car, and that charger is designed by the manufacturer itself. Okay, so that part, let me come to that. So, as I said, there are two sources. Battery as a source of energy, and their motor is connected here, and here fuel is a source of energy which drives the IC engine based vehicle. So when the two source is driving in vehicle and the one wheel is connected, let's say the front wheel, so that may be coupling through the mechanical, through individual. So that shows this particular part. So we have one energy source and other energy source, and since IC engine based vehicle is a unidirectional power flow. From the tank you can drive, from fuel you are driving the engine is driving the wheel. Okay, you cannot send power back to the fuel. But in battery case, there is a bidirectional feature is involved. Means the battery is providing energy which drives the motor is connected with wheel, and suppose some braking action takes place, rotational energy should be sent back to charge the battery. So here the flow of power is the reverse. So accordingly, while selection of the power electronics converters, you should think of how the power is being transmitted, what kind of technology, what kind of converter we are going to use. So, but ultimate aim is to drive the load. Means mechanical, it is wheel, you drive the wheel. Again, this is the same way. In some of the configuration, the IC engine is driving the wheel, and the IC engine is coupled with generator. Whatever generated energy is coming through the power converter, it will feed power to battery, to charge the battery. So you need not to have a separate charger for it. It is a hybrid charger system is there. And once the machine picks up certain speed, once the vehicle picks up certain speed, this IC engine is now stopped and the battery start providing in it charging the wheel. So that is also there. Okay. Similarly, some of the configuration is also like this. Fuel is powering engine through the generator. It converts DC, and after this DC is again converted, it is going to charge the battery. Here this DC is the bidirectional, because once you are through tank, you are going to charge the battery, and whenever this is the power bidirectional converter, so the power during this wheel is going to drive through the battery, through this battery, then converter, then motor drive, and then this system. So there are two things. You can directly drive the whole system, and second thing, you can charge it simultaneously and you can drive the system, and you can stop this engine operation and the battery start providing energy to you. So that kind of a series parallel combinations are possible. So that can be used. This is one of, let me skip that part. Again, come back to this plug-in electric vehicle. So plug-in means tank as well as the vehicle battery, both are there. So this is the case of Tesla S. Here the more general, as today the lithium-ion battery is the most popularly used for used as a source of energy. That is it. That is the one thing. Second thing, acceleration requirement is within less than 5 seconds, battery vehicle has to reach to about 50 to 80 or 100 kilometers. So there should be a rough idea what should be the acceleration time for a reasonably available vehicle. So here acceleration time is around 100 kilometers in 4 seconds, 4 to 5 seconds. Top speed around 200 to 250. Speed range up to 400 kilometers. And this is the front end wheel. So you have an idea the vehicle should be at the front side, means drivers, your converter and motor should be coupled with the front wheel as well as the back wheel if you are using both wheel drive. Okay. Now I am going to skip all this, but you just focus on some of the range, like battery capacity. See, 50 kilowatt hour is the battery capacity, and this is the torque requirement around the 300 Newton meter kilometer. Okay. Now see one more thing. Now it is changed. See here, the type of motor used for driving the vehicle. Now how much is the motor available? What are the motor available for vehicle to drive?
VFDC and PMSM.
You might have studied the DC motor is the one, then induction motor, and then synchronous motor. DC motor, it is now inferior because of the commutator brushes arrangement, but in time to come, if there is improvement, probably that can be taken over, because you cannot generalize that the DC machine is the inferior. Like earlier, similar like AC transmission, DC transmission. But 50 years before, the people were convincing AC is superior. And now the whole infrastructure is the AC transmission system, which is still existing. But now still the debate is going on whether AC is better or DC is better, because now the scenario is changed. See the generation station. All the generating stations generally located very far from the consumption center, load centers. And that was the case of the conventional energy sources like thermal, hydro. They are the location specific generation. But what is today's scenario? Now the source of generation is different because of the renewable sources. There is a solar panel you can install everywhere, even very close to load center, even at your home also. So now the generation becomes, earlier generation was very far, now the generation is very far. So we cannot generalize the DC, because since the available system is DC, you can generate power DC at your home, so you can use DC motor also. But there should be technology which can replace the commutator arrangement. Okay, that part. Then, so DC motor, induction motor. Induction motor is a very popular, and Tesla, they have used it and they are still using. Okay. And in synchronous motor category, the PMSM is the one. Okay. Again in synchronous motor, PMSM, then other motors will come. I will show that part. So type of motor used is the PMSM. And again the power requirement and everything, it is specified. So if you have a four-wheel drive system, four-wheeler, you can think of the battery rating up to 25 to 300 or 50 kV kilowatt hour. And the power rating of the motor is around 50 kilowatt to 100 kilowatt. Okay. Now see the some of the. This is also one of the motor IPMSM, interior permanent magnet. Now, if you see the synchronous motor is a doubly excited, where stator you can feed power through the stator, and simultaneously you have to generate flux, and that can be possible through the electromagnetic or through the permanent magnet. If you have an electromagnetic, then in the rotor windings should be there, then you should apply DC excitation, and then so from where the DC source will come. So again you have to think of that arrangement. So if is that replaced with the permanent magnet, then the rotor start rotating and the permanent magnet is fixed within the rotor. Permanent magnet can be fixed either at the surface or within the surface or inside the rotor itself. So depending upon that, the nomenclature is IPM-SM, interior permanent magnet. Okay, and the rest of the feature is same. This is the example of two-wheeler. Similarly, and see the power range is close to 50. Why I am showing the power range emphasizing? Because when I go to my research part, I will show I have selected this much power of the battery. So that skip. So type of the motor PMSM, permanent magnet synchronous motor, and it is used either in four-wheeler and two-wheeler. And the voltage rating, in most of the cases, the voltage rating of the battery is around 400 or close to 400. Like here, 375 is the rated voltage, and the no load voltage is higher than that, 373, around the 400 volt. And battery capacity is 30 kilowatt hour. Now coming to this two-wheeler, three-wheeler, this is two-wheeler. The BLDC motor is also popular, and they are utilized, they are used for two-wheel drive system, two-wheeler system. See the capacity, it requires the 20 Newton meter and the power range is of 2.8 kilowatt. The battery is 1.9 kilowatt hour lithium ion battery. Okay? So if you have a two-wheeler, you can think of at the most you have a 2.8 kilowatt machine. And what is the voltage rating? See somewhere voltage. The torque requirement is almost 20 Newton meter. Power is around 5 kilowatt. And the battery range is 2.4 kilowatt hour lithium ion battery. Okay? Yeah. Now coming to this part. This is the hub motor. It's a BLDC motor. And they are connected within this wheel itself. And this is also called as an in-wheel motor. Okay? And this is a 1 kilowatt capacity, and the battery is 72 volt, and the current rating for capacity is 45 ampere hour. Similarly, the DC charger, now I am coming here, you have a power capacity of 1 kilowatt motor. Obviously, the battery, if you multiply this two, it will be close to that particular part. But what is the charger rating? 48 into 3, around 120 watt. Okay? 40 into 3, 120, 125 watt charger. So what I want to say, if you have a 45 ampere hour battery and you are charging with 3 ampere current, how much time battery will take to charge fully?
9 hours.
It's 9 divided by 45. Okay. So around 13. 45 divided by 3, it gives 15 hours. So you require an overnight charging, and so here the charger is slow. Because this is a dedicated charger you have made, and their current rating is fixed. It is a 3 ampere at the most it can charge. But if you have designed, suppose if you are designing charger with a very high power rating, let's say 45 ampere, then what is the issue? With 45 ampere 48 volt charger, you can charge within 1 hour. Okay? But again issue is the size of the charger, cost of the charger, it will be bigger. Okay? So that is the issue, and how to curtail that part we will discuss in my further some of the research. See here, this is the one of the Hero Electric Plus specification hub motor. It is used somewhere Then 48 volt battery with 24 ampere hour capacity, and the power rating is 240 watt. Okay. Same way. So in general, you can make a rough case. If we have a two-wheeler, you can battery voltage will be 48 volt, current rating will be capacity may be 20 ampere hour, or it may be 40 ampere hour. So this is the case. In four-wheel, it will be 50 kilowatt charge, 50 kilowatt battery, and around 400 volt is the capacity of the battery. Okay, and here lithium ion technology of battery is same. It is a lithium ion. See some of the case where 60 volt 20 ampere hours. So capacity you can fix up 20 ampere hours, and the voltage may vary from 24 volt to 72 volt. Okay. So again move to the three-wheeler. What is the three-wheeler option? The BLDC motor is used. The power rating is over 1 kilowatt. In two-wheeler it is less than 1 kilowatt. Here 1 kilowatt to 2 kilowatt is the range of the power. And the voltage rating is 48 volt. 100 ampere hour is the capacity. Okay. And the lead acid battery. Again, you have to see the cost component, because the lithium ion is the costlier as compared to lead acid battery, and at the same time the size is bigger. So here we have no space constraint as compared to two-wheeler. So we can put a battery either at this cabinet or the back cabinet, wherever you want. Okay. So again, it is a lead acid battery. Current rating of 48. Battery rating is 48 volt 20 ampere, and this is a little lower rating of the power. So this way I try to cover four-wheeler, two-wheeler and three-wheeler, and you have a rough idea what should be the rating of the battery, motor, and then the power rating of the machine. Okay, now coming to, let me move faster because I have a number of collections. This is skipping. Okay. In contrary, I have this. You see, we have induction motor, we have permanent magnet synchronous motor, IPM, SM, and that are the motor used. This is also one of the motor which is very popular, but not being used because it has some other constraint. Switched reluctance motor. So, but still the few manufacturers they prefer this. But again, it creates sound. But it is that sound is still it is less than the sound of IC engine. So some of the vehicle, a very old vehicle, they are using this switch reluctance motor. I'm just skipping that part because okay, now coming to the charger. So if you see the charging infrastructure, our source is the AC. Battery which is to be charged is operate with the DC. It means we have to convert AC into DC. Now, since let's say any example for the two-wheeler, three-wheeler or four-wheeler, let's say the two-wheeler 48 volt battery you want to charge. So if you want to make 48 volt DC from the 230 volt AC, you have to convert AC into DC. And now there is no converter. Can anybody tell with a single phase AC supply, you have a 230 volt, I want to make 48 volt. What is the general conversion component? What are the steps required to convert 230 volt 50 hertz single phase AC to 48 volt DC? You have to step down to make the volt AC voltage lower, and then use diode rectifier followed by the large capacitor. This is the basics. Okay. So when you step down to the large transformer having the line frequency 50 hertz transformer which is available, so the first problem comes is the size. This size shows the this a bigger, this component is this is a larger than even PC. Okay, so this is the issue. So line frequency based battery charger is available. It will be available locally in the market, and they will claim it is the most cheaper. But it will be heavier. It will solve your purpose, but it will propagate many problems in the other side, which is not accepted by the either industry or good person who is know about the power quality, power issues. So that part. Second is the SMPS based charger. Okay, in that case, the 50 Hertz transformer which you are stepping down to some reasonably low voltage, that is eliminated. You can use diode rectifier. Okay, so in first stage, if you have a 230 volt supply, you convert into DC using diode bridge rectifier followed by the large capacitor. And if you do, you will get the DC voltage, and maximum how much voltage you will get from a 230 volt 50 hertz supply? 324. How the 324 comes? Any student? कोई student ही है इसमें? Yes. So 324 volt कैसे आया? If you see diode bridge rectifier, and you use large value of capacitor at the DC side. So the maximum, the voltage you can charge the capacitor is the peak voltage of the supply, and that is 230 into under root. So that you can keep at the most 230 into under root 2 as a, but that is a hypothetical case. Okay, and your task is to get 48 volt. So again you required one converter which convert 325 to 48 volt. Okay, so that is a rough estimate. Will detail we will see. So here you have a diode rectifier, then capacitor, then some DC to DC converter, some isolation may be there. So that is the SMPS based charger. Okay, and so still I am skipping this part, but see what best we can take from here. This rating of the battery. So as it is an auto rickshaw, the battery is 48 volt, 100 ampere hours, and this is the motor, 48 volt and 15 HP motor. Okay. So what I want to tell, either it is two-wheeler, three-wheeler or car, their motor rating is higher than the battery charger. Their power converter, which is used to drive the motor, they are also rated at least more than the rating of the electric motor. Okay, and so now, what should be our expectation? Because the electric vehicle is act as a source of energy. Like battery is there, and battery is a source of energy. So one thing, you can charge the battery. So that is we are calling, and you are charging from the power grid. So that is called the grid to vehicle. So that is very popular. Everybody knows. But you can use as a source of energy, as a distributed energy source. Suppose on the road, if a number of cars are coming, and in future it is expected to come, it may compete the IC engine based vehicle. So they can be act as a source of energy, provided while charging you are taking power from the grid, not from the grid, from other source, like from renewable, from solar panel, you can charge it, and you can, once the battery is fully charged, you can use as a source of energy, and you can feed power either to grid, because there are many states, though Gujarat is good in electricity, but there are many states where the electricity, we are facing problem of electricity. Even we are not getting 24-hour, 12 to 18-hour electricity in a day. So if the battery of the energy is charged, battery is charged through the other source of energy like PV panel, windmill system based energy, and you can feed power to grid. or you can feed power to local load, you can feed power to home, you can feed power to other battery vehicle. So that way the battery operation can be, means motor electric vehicle operation can be optimized, and therefore this can be called as V2X. X may be the load, it may be home, it may be vehicle, it may be grid. So if you have a battery source as energy which can be charged from the renewable sources locally, that can feed power to grid, so that is called vehicle to grid. Now the vehicle can feed power to local load, your home, so that is called the battery vehicle to home, or vehicle to local load, isolated load, some remote place where you want some sort of energy, that can be done. It can feed power to vehicle also, vehicle to vehicle operation, so that can also be done. And is and the charging, obviously the charging is smart. Smart in terms means it should be sustainable. It should not be like that you charge power from the grid and you can feed power to grid. That is not the optimal. You charge from the other source of energy and feed power to grid. And in the process, you need to strengthen your meter, because meter should not be the conventional meter, it should be bidirectional, smart meter. So metering is also important. Communication protocols should be followed, otherwise charging will not take place. Suppose you have designed the charger and you fit in the battery, it will not work, provided the other communication protocols to match. Okay. So that's enough for the just schematic diagram. Let us move to the next part, where I have some efforts to make the system in our place. So as I said, that there are two issues, battery technology and the charging infrastructure. Now, the battery technology mostly used, whatever you have seen in the practical situation, either it is the lithium ion is somewhere here, and the lead acid battery in three-wheeler, it is around here. So if you see the power density, power per kg weight of the battery, obviously the lead acid battery is the poorest one, and the lithium ion is about 10 times efficient in terms of their weight. It is lighter, 10 times lighter than the battery. So second, the number of charging life of the battery depends on how fast you are charging, discharging, one cycle of charging, discharging. So that lead acid is around 500 cycles, whereas the lithium ion is around 100 to 1000. So almost double the life of the battery, and the size is big. So that is why today the lithium ion battery is the most popular as compared to the lead.
The life of the battery.
Number of
Charging cycle.
it reflects the life of the battery. Any battery, how much time it will be there. So if you charge for 100 times and discharge, its life will be fixed. Now coming to the general layout, this is a four-wheeler, and the general layout is we have a battery pack here. Then there is a bidirectional charge, a DC to DC converter. I hope you know the power electronics, DC to DC conversion, AC to DC conversion, that all you know. So here battery pack is the DC, and through the bidirectional converter you can convert DC into another DC, and this is the DC point. This DC is through inverter because motor is AC, so you have to apply AC supply. So there DC to AC converter, that is called the traction drive, that word is there. So basically this is the inverter, voltage source inverter, that will convert into AC and it will drive the electric motor. Electric motor is coupled through transmission system, through wheel. Now this motor is also fitted in the wheel. So in that case the transmission system is finished. No more. So, but here you just as a sketch, you can assume that there is a wheel which is coupled with the motor and it is a driving. Now, obviously the DC supply which is available here as the input of the inverter, that can also be used for the other accessories like lamp, AC, etc. for powering, you can get it. Now, when the machine is running as a motor, the flow of power is from the battery through the bidirectional DC to DC converter, then through inverter and through motor, only this part. And there is a one wheel drive system. So then let's say the front wheel, the drive is connected. Now the second case, if you see this particular box says that the on-board charger. So as I said, plug-in electric vehicle. So this charger, on-board charger is placed within the vehicle itself, and the vehicle is running on the road, and suppose if they require charging, they can park and they can put their charger at the convenient place and it will charge the vehicle. So this is the just schematic diagram of a plug-in electric vehicle. Okay? Now same thing with another form. Here we have a AC to DC converter which is an on-board charger. Earlier it was here. Now the same thing, here is a AC to DC converter. So either you can fit it at any place and it will going to charge your vehicle through the DC to DC converter to the battery. So if there is an electric vehicle, you can use its own dedicated on-board charger and you can charge it. Okay? Suppose you do not want to use this AC charger, on-board charger, because on-board charger, its rating is very less. I said in that one of the case, let's say the two-wheeler, the charger is around 125 watt, where the machine was rated for around 1 kilowatt. So this rating is very less and it is a slow charger. It takes around 5 to 10 hours to charge your battery. But suppose you want you want faster charger, then this battery can be charged directly to the DC, and here it is called off-board charger. Off-board charger means, suppose one person has set up a business of charging, they have installed charging facility near to their parking area. So there you can directly plug in this to directly, and here it can charge. So this part is located outside the vehicle, and you can just make the communication here and you can charge the battery directly. And that can be charged within 30 minutes or 1 hour, your battery will be fully charged. So, but here you have to pay higher charge as compared to this. Okay? Now, so as for the level of charger, there are basically 3 levels of charging. We call it level 1, level 2, level 3. And these chargers are based on their power rate. As I said, the level 1 and level 2, level 1 is a slow charger, like two-wheeler charger. It takes around 5 to 10 hours or 15 hours to charge your battery. So this is the onboard charger. And the rating is obviously very slow. This is with the four-wheeler discharging rating. Similarly, the level 2 is also of it is onboard, and based on their charging power, like it's a 4 kilowatt charger, 8 kilowatt charger. If it is a 4 kilowatt charger, you can use single phase supply and you can charge your battery. But if you are going near to 8 kilowatt or 19 kilowatt charger with an 8 ampere current, rating of the current, then you have to use 3 phase supply. So that is why it can be used with single phase or 3 phase charger, so that is also available. So my work, initially I started with this level 1 charger. Now I have shifted with level 2 charger, and that can be used up to level 3 charger also. So that topology I have proposed, which can be go up to 3 type of charging. Okay? And the charging timing are also given here. Power, this technology, why I am putting this? because they are related to the specification of the different vehicles which we have seen. Now, this is a simple case. The onboard charger, which is placed within the vehicle and it can be charged to any, this is called AC charging because you are fitting to AC supply. And the AC to DC conversion happens within the car itself through the onboard charger. Whereas DC charging, it provides DC terminal and it is going to directly connect to the battery. While conversion, one term is important, that is called BMS system. BMS means battery management system. Without it, no charging will be carried out. So the role is it will ensure the SOC of the battery, what is the state of charge of the battery, what is the healthy condition of the battery, life of the battery. At the same time, what is the driving condition, whether the vehicle is running or some fault are there. Everything, if it found okay, then the charging start place. So, apart from the power cable, there is a control cables also. So, the BMS will ensure all the proper condition of the battery and then the charging will start. So, while charging, you require charger as well as the BMS system together. So, now coming to the first case, let's say I have a simple off-board charger. Off-board charger means, suppose I want to set up a business near to my home and there is a one parking lot. So I can use, say in my home, let's say we have a single phase supply. It is given to your residential load and then I am using a simple, since here is your car. So obviously if it is a 48 volt battery, so first AC is converted into DC. That DC is not necessary, it will directly 48 volt, it will be some value, and then we use DC to DC converter to charge the battery. So we required AC to DC converter, PWM converter, and then DC to DC converter to charge the battery. So this much infrastructure is required. Okay. So what I use, I required, you remove this dotted portion, this two converter is required at my place. When the battery comes in, the charging will start and it will charge the battery. So this is the one topology that I will show at the stage. Now this is the topology which is available within the car. I said the manufacturer of the car provides onboard charger. So in onboard, you are, let's see the configuration again and you. Yeah. Let's say this particular part, AC DC charger, then PFC converter, and then DC to DC converter. So this part of a converter, it is within the vehicle. So this is called the onboard, and this is designed by the manufacturer, not by the local market. Okay. So this converter topology is something this one. I have a AC supply followed by diode rectifier. It will convert into DC. Then here we can use non-isolated or isolated PFC converter. So the first stage I will convert AC into DC. Now I said in the beginning, if you have a diode rectifier followed by the large capacitor, it will not, it will do your job. It will convert AC into DC. But that is not being accepted in the good platform. Like suppose at international market, if you want to sell it, they will say you have to follow certain regulation. Regulation may be IEEE, it may be IC. So this all regulation, BIS, that all regulation you have to fulfill. So if you convert AC into DC at this particular stage, a first conversion required, you have to comply the grid. Means you should not generate harmonics in the grid. Number one. And then in the quality of power, you should not distort the power supply. Okay. So here you have to make AC-DC conversion. At the same, here the quality of DC should be smooth, almost constant, ripple free. At the same time, this input side, it should be good power quality. Okay, I will show in the simulation section, that part I will be going to cover. Okay, once you got the DC voltage just prior to this DC to DC converter, here battery can be charged. Let's say the battery is fully drained. Suppose battery is fully drained. Moment you connect to DC supply, what will be the operation? The current will be limited through their internal resistance only, and the internal resistance of the battery is a little small, so it will draw heavy current from the supply. Okay, so it will draw more current from the supply. Suppose battery is discharged or fully discharged, it will draw more current, but you cannot allow any current from the source. You have to control it. So first you have to discharge, you have to charge the battery with the constant current charge. Because that current you will decide, like 48 ampere hour is the battery capacity, I am charging with the 3 ampere capacity charger, so means 3 ampere charging is fixed. It cannot provide current more than 3 ampere. So here you will get 3 ampere charging and it will charge the battery. Got it? So this is the situation. So the two-stage conversion, AC to DC and then DC to DC conversion. Got it? So what I did, this is now the work started from my side. I used diode rectifier. Then there is some DC to DC converter. I will not discuss here because very general, it will become more general. But you just have a feel. Here AC to DC converter, and then this is the charge. This part of the converter is used to convert AC into DC to comply the power quality issues and make the system ripple free. So this converter is replacing only the first stage of conversion, or it can be used as a onboard charger of the battery, which is designed by the manufacturer itself. Okay, and normally the controlling is done like this. As I said, when initially you have to charge with the constant current. So when you charge battery with the constant current, the charging starts and SOC voltage keeps on building. So state of charge keep on increasing. Moment the state of charge becomes more than 80%, 90%, you have to switch operation from constant current to constant voltage, because the voltage is also keep on increasing with a slightly lesser rate, and current will keep on decreasing, because once the battery keep on charging, it will allow lesser current to flow, and at one moment the current should be very less than 1 ampere, less than 0.5 ampere. Then you have to make the voltage constant and you can keep the current settled. So that is the process. So almost 90% of your charging, the constant current charging, the lower block of the converter this control will operate, and depending upon the state of charge, this constant voltage charging will initiate, and that will going to turn on this switch and it will start the charging. Now why we are doing this, otherwise the first topology like line frequency transformer based charger can also do the same. Here see the voltage and current rating, voltage and current waveform, see the voltage at the DC side, that I will going to show you. I am skipping this part, these are the technical. Now see what I want to show. See at this particular stage, this is the voltage waveform, which is sinusoidal. These are the practical waveforms of the system. So this is the voltage waveform. Normally AC is sinusoidal, and their current at this just below this green color, this current is sinusoidal, and they are in phase. Normally we expect when you are drawing current from the source, the voltage and current, those must be same phase, and that is the good charger. So this kind of waveform should be there. At the same time, if you see the DC side, this DC is the constant, though it has a ripple. If you see, its ground line is somewhere here, and this line it is fluctuating. So normally ideal DC is the constant DC, which is the ideal. But if you see, it is fluctuating around the DC. That is, it's a fluctuating. So that is called the ripple in the DC. AC component within the DC component. So this should be smooth, and obviously the current is resistive. So this current is the constant. It is same reflection. So what I want to say, whenever you test any charger, and if it should be meet the international market, the voltage current which is drawing from the source AC side, it should be sinusoidal, and their THD should be less than 5%. If you are charging from the 230 volt supply line, okay. And the rest of the things I will not go in detail, because at this stage you just focus on the AC side as well as the DC side. Got it? Same way you can see I have a 500 watt load I am feeding to that converter. So see, this is the AC supply, voltage 230 volt, and this is called the DC. This green color is the AC, and both are in same phase. At the same time the voltage is reaching peak, at the same time current is also reaching in the peak. So this way you can judge the PFC operation. We call it power factor improvement at the input side. This is the DC waveform, DC voltage, and this is the DC side current. Okay. Now, one more expectation. Suppose if there is a fluctuation in AC line, because you have an AC, you are converting into DC. AC control is not in your hand. Yes.
There is ripple in the DC voltage, so if you charge the battery, then it will not be a problem for the battery.
See, this is the, let me go to that part. This converter, this converter I am talking only the first stage of converter. Means this point, we have a DC which is having ripple. Again we have a DC to DC converter here. So that will going to make the other charging, like it may be constant current, and it will ensure the proper. So that is that conversion is only AC to DC. This part is still I have not explored. Okay. So this is only the first stage. Second stage is still pending. So where is that? Here. So what I want to tell, whenever you design any charger or any battery system, any power supply, the first requirement is it should provide constant DC voltage, irrespective of change in input voltage, change in load. Simple. If I have a grid voltage here, grid supply here with the 230 volt available at the point. Suppose if I add one fan, I add second fan, so voltage should not drop. The voltage around each plug should be 230 volt. Okay. The same way I did here, there is a change in input voltage. Somewhere there normal voltage was there. Suddenly voltage is decreased to 180 volt. And while doing that, see the DC voltage earlier it was this one. Now moment the voltage is reduced, it will dip slightly and again it resumes to the same value. So that shows the line regulation. If there is change in input voltage, your output should not change. Like even your mobile charger, when you plug in, when the voltage becomes 230 volt or 200 volt or even 110 volt, your battery output should be, if it is a laptop, it should be 19 volt operation voltage. Okay, so that should be there. So that part. Similarly, if you want to increase the load, like I said, in this wall, if I glow one light or second light or all light, the voltage should not disturb. So here also you have seen, if I increase the load, the output voltage of the battery, it should remain constant. It happened with a slight disturbance, but it resumes its normal healthy position. So that is the way to test the closed loop operation of the system. Okay, this is the steady state case. Here now move to the, as I said, it should meet the quality standards. So see, when I am either operating with 84 volt DC AC supply or I am operating with, let's say, the 230 volt AC supply. See, when the voltage is reduced, 84 volt, it is drawing 50 hertz supply, it is drawing 6 ampere current from the supply. When voltage of the supply is 230 volt, like this is 230 volt, it is drawing 2.3. So obviously when the voltage will be more, current will be down, but the total power going to the load should remain same. Okay? So now see the power level, 500 watt capacity, active power is 0.51 kilowatt, 500 watt. And same way, see the THD, input power factor is unity power factor. Like normally this converter is called UPF, unity power factor converter. THD in voltage, normally it is less. See THD in current, this one, yeah, 6 ampere is the current. So THD is 4.8. The 4.8 shows that it falls below the range of the PFC converter. Here, as per the regulation, PFC should be less than 5%. So that way it is given here. Even if you increase the voltage, under that case also, the voltage is THD in supply is less than 5%. So this is the one of the converter that I did it. Now this is again some modification and same converter, which I am not going to talk here only, because one is enough to understand the concept. Same thing with another converter, and it also meets. Now let us move to this particular. The previous converter I talk about, that is an onboard converter, normally manufacturer design, and it placed in the car itself, and you are charging the vehicle onboard. This is the off-board converter. I said, let's say this is the single phase supply available and it is feeding to my home, and I have a dedicated this converter available at my place. Whenever the vehicle comes, the charging starts from this grid to this, and whenever this vehicle is absent here, no vehicle is there, then this should not kept idle. What I want to say, this configuration shows that this charging infrastructure is available, but whenever the vehicle is available, then the charging will start. If the suppose vehicle is not there in the parking, there is no point of charging. And if this system is available, why not we use this system for some other purpose? This is also there. Sometimes suppose the grid is not available, let's say the grid is absent, no supply available in the grid, then this vehicle power should feed power and it should give to this load or to home, like vehicle to home application or vehicle to. So that all part I did in our laboratory, and that was same. This is the one case. So second case, here we have a 3-leg of inverter, and in power electronics we have some more this one leg can be removed using single phase half bridge PWM converter. So see the next topology is like this. As far as this part is concerned, this is there, but this part is absent. That I will do in the simulation in the afternoon session. So that will see here one leg is absent. This capacitor which is already there, I can use 2 capacitors connected in series, and which can fulfill the same amount as this capacitor. So if I do this, one leg can be removed, and this half bridge converter along with this filter and this converter can do the same operation as this. Only the problem, only the new thing for this is the control algorithm. What is the 3 control algorithm? What I want to tell? Whenever the vehicle is available and it requires charging, it demands power from the grid and it will charge the vehicle like this. Again, when it goes like this, the first stage it will convert AC into DC. Second will do the DC into DC as required by the battery as per the SOC requirement. Constant current charging, constant voltage charging. Now second thing, when the battery is not there, vehicle is not there, then this capacitor is the self-supported capacitor, and it will feed power, means grid is giving power to residential load. So the role of this is act as a compensator. You might have studied the D-STATCOM. The role of D-STATCOM is to provide the active power support, reactive power support to the grid. It eliminates harmonic. So all type of operation can be done if there is no grid available. So this is not become ideal if no battery is available. It can be operated and it can work as a harmonic filter. It can provide reactive power compensation. So all operation can be done here only. And whenever grid is available, suppose grid is not available, then the battery power can be feed power to residential load. So 3 operation I operated with the proper control, and this is the general proper control for that. Okay? So this part, the lower part is same as what I said. It is the battery, you have to sense the battery voltage, battery current, and then that pass through the PI controller, and it will generate pulses for the this converter. Okay, and this upper side is used for PFC operation, so that can be done. For controlling this particular half bridge up converter, and the same control can be done for this particular case. But the things which I want to show at this gathering is this is some system parameter like 230 volt, 50 watt is the supply, 500 watt, 400 volt is the battery capacity, and lithium ion battery of 400 volt, 12 ampere hour is the battery which is available in our laboratory, and these are some specifications. See this particular part. This is more clear as compared to the previous converter. See, this is the voltage waveform which is almost sinusoidal, and the current is also of same nature, having high ripple, and they are in same phase. If you see, the voltage and current both are in same phase, means from the AC source current is power is feeding. Okay, and now see the THD aspect. So here the THD is 3.5%. 3.5% is the THD in the supply side THD. Okay, what else? See the DC voltage and the DC current. Here current is negative. Means now this is the positive, this is the ground line, so this is the positive current. Now see this particular part. Constant voltage, it is same as what I did. This is also same. Now see this particular case. Can anybody tell what is the change in previous this case and in this case? What is the change? Yes? Student side. See, if you see this battery voltage is positive, blue color, and the current is negative. This is the midpoint, current is negative. See here, current is positive, battery voltage is red color, it is positive. See here, the voltage is AC side, voltage is sinusoidal, current is in same phase. And now see the previous case here, not there. This one. What is changed? Voltage is this blue color is the voltage of battery, and current through the battery is negative.
Charging and discharging.
Yeah. So see, that can be see here. The AC voltage, sinusoidal, here it is out of phase. If you superimpose, here the positive half, here it is going down. If you see the power quality this side, here power is negative, minus 256 watt. This shows that you are feeding power to grid. Means car is available, load is available, and there is no power available in the grid. Yeah, even the grid power is available, but the excess power of the battery is going to feed to the grid. Okay, so that operation it is going to show here only. Now same thing, this shows the harmonic operation. Suppose if the grid is not okay, if grid, this is the compensating current, it is going through the system, so that part it is showing. So in the event of no power available at the means no battery is available for the charging, only the capacitor will provide the reactive power support to the grid, so that it all the time it will draw sinusoidal current and in same phase with the supply. So that should be the same. Okay. So that one part, and one more thing. Okay. So that previous converters I just talk about a single home that can use that converter, inverter and the battery system, and they can do their job at their place. Now this is the place, suppose you have a one parking area where 4-5 cars can be parked together. So this way, same converter, we have a single phase supply feeding residential load. But if it is a parking lot where suppose I want to design 5 kilowatt charging station, in that case instead of single phase, we can have a 3-phase supply. And same way, when there is a 3-phase supply, here it should be 3-leg inverter, and they can do the 3-phase operation. But since in our laboratory there is a many constraint, we cannot go for the 3-phase supply, and then the voltage level will be the problem. I have realized the same concept with the single phase supply. Okay, so we have a single phase supply feeding to residential load, and this is the one single phase inverter, and through the one filter inductor I am going to charge to the DC. Okay, so it will convert AC into DC. So here you got the DC. That DC may have a fluctuation, 5% deviation, or even you can make it well regulated, no problem. Now, here you can use a DAP converter. Normally the DAP converters are very popular, and today we have 6 devices which can be operated to 100 kilohertz switching frequency, or even 250 kilohertz switching frequency. So this can replace with a very miniature size switching converter, and you can do the all operation. Or even you might have wireless power transfer. So since this is a high frequency link available here, so this much infrastructure you can make at your parking lot, like on the road or on the near to highway. And this 2 coil which is separated by some space, that can be fit in the slab of the parking lot. This part, this remaining part, second left right side of the converter and all, that should be available in the car itself. So whenever car goes for the charging, it will park there, and then the charging start place. So you need not to have any communication, but that can be done. So there is a feature you can operate it with the wireless charging system. Okay. Now moving to, so this is for the one vehicle, this is for the second vehicle, this is for the third vehicle. Like that, as an instant I shown only the 4 vehicles which can be parked together. If none of the vehicle is available for the charging, again this capacitor along with this only configuration can do the power quality issue, like reactive power compensation.
First one is active rectifier.
Yes, first one is the active rectifier, which has the capability to feed power to both the sides. While charging, it will take power from the grid. While discharging, it will feed power from vehicle to grid or vehicle to home. So that can be.
Synchronization is also.
Yes, operation of this is through the synchronization of it. And if the time permits, I will show that particular, this small converter and their operation at a laboratory station. Okay. So this also we have tested. One of my students, they did it, and again same thing. I will not touch much. Now this is the more specific. Let me go to one more presentation, and then I will cover this part. this is the current work which I have done 1 year before. Okay, so this is called the integrated onboard electric vehicle. So why it is integrated? As I said, the government cannot set up charging infrastructure to every door, yeah, at every place. Off-board charger can be placed near to your home, near to some specific locality, and whenever you require to charge, you have to go there and charge. But if this can be added, integrated facility in onboard charger, if it is added, that can facilitate every vehicle to charge everywhere. Only the requirement is the power supply. Okay, means if the convenient port is available, you can park your vehicle there and you can plug in and you can start charging. So this is, and one more thing, I said onboard charger normally designed for the rating of 2 kilowatt or even less, yeah, 3.3 kilowatt. The reason being, if you start designing onboard charger, like manufacturer will decide the capacity of the charger, it will take larger space in the battery, in the vehicle, and therefore the vehicle becomes more heavier. Okay, and mileage becomes, it will be slow. So how to facilitate this kind of operation, that we are going to talk here. Before I start, a very small, we have initiated one startup in 2021, and its name is Smart Charging Solution. It is a MSME, and we have developed few kits like power electronics rapid development kit, custom power converter kits. Some are already patented, designer patented, and IGBT and 6-base drive circuit. This was it was the outcome of some of problem during Corona. Before Corona, we used to buy gate driver circuit from China, and due to Corona, everything was stopped. Then we have started reverse engineering of that kit driver, and now we have made our own driver, that is the IGBT gate driver circuit. That becomes so popular, it covers around 15 to 16 institutions where the research scholars are working. They have ordered, and we are successfully, even today we are getting order from some of the good institutions, particularly the IIT I am talking about. So sometimes you have to do the reverse engineering. You have to borrow single item from some other place, do the reverse engineering, make your own contribution and make your own system. So that was done, and now it has become very popular. You can move to this particular scspower.in is the website where you can get it, all the products what we have done till today. So that is already available, and so this is just for information. Okay, so here I'll be going to talk about the integrated battery charger and then onboard charger. Onboard charger means it is the same as in the car the charging is there, but we are going to utilize, we are not going to add any extra component in the system like the existing system is. We are going to utilize the motor winding, we are going to utilize the inverter of the motor which is used. I said in the very beginning, the size of the motor is of the 5 kilowatt. For 3-wheeler, the size of the motor is 3 kilowatt, 2 kilowatt. And the converter size is more than the motor. So in short, I can say the rating of the motor is very high. It can carry any amount of current. Okay, there is no issue of wiring, there is no issue of plug cabling. So why not we use induction motor or the PMSM motor and their inverter for the charging purpose. So here we are using same motor for the charging purpose, that I will going to tell, and that will do all the power rating requirement which was recommended for this off-board charger. Okay, so This was a separate talk, so that I am clubbing here, but our interest is so that was a replication of the same diagram. As I said, this particular part is the onboard charger, and it was normally designed for the manufacturer. But in this case, as the name suggests, it is an integrated charger. Why not we remove this part? Why not we remove this entire part which is placed in the vehicle itself by the manufacturer, and we can use this component like motor winding, this inverter winding, because whenever you charging, you go for the charging, your vehicle is at the rest, it is not operational. Then you can utilize this winding, this inverter and this converter for the charging. So now I am not going to use this part, even it is completely removed, and this is charging start from this part only for this component. So by doing that, you can reduce the size of the converter, size requirement, even the cost cutting of the charger within the vehicle itself. So, and the same thing can be reconfigured like this. So, suppose during motoring operation, we have a battery, then DC to DC converter, then it's an inverter, and this motor is driving wheel. So, when machine is running on the road, vehicle is running on the road, the battery is going to power the motor through this flow, left to right. But whenever the charging is required, then you can tap the winding of induction motor and you can plug in the vehicle here, and you can feed power back to source. So that was the integration. So the same converter which was there during the motoring operation, during charging operation, the same converter was utilized. So see the one more figure which can give the better feel. This is the one. So this is the battery, like let's say this is the DC link voltage and this is the inverter, it is driving a motor. Same configuration is like this. There is a battery, there is an inverter, and three phase is connected to stator winding of the motor, and the motor is rotating. So during motoring mode, the battery supply energy to motor and motor starts. When the battery is required to be charged, you have to take, let's say this capacitor midpoint, one wire is there, induction motor neutral point, one wire is there, this two wire is connected to the charging socket. And you can plug into AC supply like this. So now what is happening here? The AC supply is connected to this part and the one supply is connected here. And the operation of this converter is as a PWM, three-phase PWM rectifier. What is the new? Induction motor winding, this inductor winding, they can be act as a filter inductor. So induction motor winding is acting as a filter inductor. Okay, so that part we have done it and it is working successfully. Okay, let us see one of the small video and then I will come back to the same part. Same operation what we did at our place, where this battery is replaced with the one resistive element. Okay. See, this is the induction motor. There are three-phase winding, and now this AC supply is connected to this VSC, and this is connected to this resistive load. This when no charging start, it is 72 volt DC is available. There are some sensor, some controller. This is STM32407 controller. Here 65% THD is there. This is the input voltage, input current waveform. Now we have turned on the supply of the gate. Now current becomes sinusoidal and THD becomes less than 5%. Okay? So THD becomes less than 5%. See the voltage and current almost sinusoidal. almost sinusoidal current and voltage, and see the complete voltage waveform, and the voltage becomes 110 volt, near about 109, 110 volt, 9 volt DC we are getting. So as a prototype experiment, what I did, from AC, single phase AC, I am converting DC of 110 volt following the AICTE regulations. Okay? So this setup we have run, where the three-phase induction motor winding is utilized as an inductor, and this VSC is operating and it is feeding to the resistive load. Okay, so that part we did in our laboratory. Same, see, this is the four-wheel drive system. As I said, in-wheel motor, each wheel of the machine, here we have a four-wheeler, and the front wheel is having two induction motor like IM1, IM2. It is coupled with this vehicle, this wheel itself. Okay, here it is also coupled with the vehicle, and now there is a dedicated inverter. This VSC1, VSC2 is the dedicated inverter for each motor, and now there is a DC link. So this battery pack is providing energy to this part. Similarly, at the rear wheel also two wheels are there, and each wheel has its own induction motor powered by their VSC. Got it? Now, when the motoring operation takes place, like vehicle is running on the road, so this battery is going to provide energy to all vehicle, all wheels, and they are operating. Whenever they are required, it can go either straight or backward. You can stop one way VSC, you can go for the back side, rear side vehicle, it will start. All operation it is possible. Now, suppose your battery is drained, and in that case there is no connection at this point. Battery is providing energy to all the four motor independently, and their operation is synchronized. Okay. Now, whenever this is starts required charging, then what happens? Problem comes when you are going to charge. So, what I did, when you are going to charge, yeah. So as an illustration, I developed two, because in my lab there is no 4 induction motor, 4 VSC. So I scaled down. I make one induction motor, front wheel with one induction motor coupled with this vehicle front wheel. This is the back rear wheel with one induction motor, and then they are dedicated in machine. So here is when the charging is starting, there is a switch I can make at P, or I can connect the switch K1 as C. P means propulsion mode. Suppose when you are going to charge the on the road, then you have to connect this socket. Driver will connect to this P, and this part is not connected. It will kept open. So the vehicle is running on the road, and power is the whole system is powered by this battery pack. Okay. Now when the battery is drained and it is expected to be charged, you have to stop the vehicle and you connect this K1 to C. Moment you connect K1 to C, this AC supply you have to connect to grid. So means the driver will move in, kept the vehicle in charging mode, and this connector you have to connect to the socket where it is to be charged. So what will happen, moment you connect to this, the first configuration is AC supply, then 3 inductor, and then 1 VSC. So this part of the first VSC and IM, they will convert AC into DC, following all IEEE regulation, what I demonstrated in our laboratory. In the second phase, whatever DC supply is available, that is going to connect to the 3-leg inverter, and each midpoint is connected to winding and it is connected to battery. So if you see the rear wheel motor and the VSC of a rear wheel, they will act as a 3-phase buck converter. 3-phase, that is called multi-phase buck converter. Okay, so this will work as a DC to DC converter, this will work as a AC to DC converter, and this will ensure CC/CV charging. So as a one illustration, this part I showed, I have shown this part, AC to DC conversion. Let's see the same thing. Okay. So let's see this particular part, DC to DC conversion. Okay. So that this is the same motor. This is the 448 volt let me show. Here we are getting the DC link diode. This is we got the DC link, and then this is the inverter card, 3-leg inverter which we are receiving, and it is going to charge this battery pack, 48 volt 7 ampere hour battery, and there is a intermediate winding. Some sensors are here. That is not part. Let us go for this induction motor. So this induction motor, it will be act as a rear wheel machine, and this winding is utilized, and it is going to charge that particular way. So let me start it again. So this shows the DC to DC converter where the machine winding is acting as a DC to DC conversion. This is so that each winding current, motor winding current, which is interleaved in nature, that is again a technological term which is more specific. I will not go in that part. So this is a 3-leg inverter followed by the winding, and it is going to charge this particular battery. And 110 volt is the DC link that we are deriving from the previous converter. So the output of previous demo was connected as an input for this demo, and the both machines were integrated to make the whole system.
Sir, what was the switching frequency during this conversion?
Let me show the specific. It's a 5 kilohertz or here 2 kilohertz I think I have made, because the inductor of the motor is very large. It is around 30 or 40 millihenry.
Yeah, they are very large as well as I think it offers the electromagnetic configuration. No?
Let me show that the specification that will be somewhere. This is a different, same topology that I have. Let me show the specific. Here, somewhere in appendix. This is 20 millihenry is the inductor of each winding, and the frequency is switching frequency is 2.5. Even with 2.5, so let. So what I did in previous converter, so the first is here we have used front wheel, their in winding and their VSC as a AC-DC conversion, and the second wheel their motor and their VSC as a DC to DC converter. So here in the process we have not used single extra component. In previous case you might have seen there is a dedicated, manufacturer provide dedicated onboard charger which was designed for, let's say, the 3.7 kilowatt charging at their vehicle itself. But here you need not require any vehicle, and that is why it is called the charger, integrated onboard charger. Okay, so same thing if you want to go for exclusively this configuration, because this configuration I have not yet commissioned. I have not tested right. But here two AC to DC converter can be done. First this two and this two can be done, and it will provide a DC supply. Okay, and this second side you can use, instead of 3-phase buck converter, you can use 6-phase buck converter. So if each phase is designed, suppose each induction motor winding, I said it is rated for 50 kilowatt, what will be the stator winding current? If you calculate for the actual motor which was in vehicle, if it is designed, motor is rated for 50 kilowatt rating with 415 volt line to line, what will be the current rating? It will be rough case 20 ampere. Let's say if it is a 20 ampere, means this winding, one winding can withstand 20 ampere current. Such 6 windings are connected in parallel if it is a multi-phase buck converter. So 20 into 6 average. So 20 into 6 around how much? 160? Huh? 20 into 6, 120. 120 ampere current you can push to this battery to charge the battery fast. So if you have a 120 ampere hour battery, with this configuration you can charge 120 ampere current simultaneously, and you can charge the battery within 1 hour. So if your power supply is available, grid power is available, this is the fastest charger you can design without extra charging infrastructure in the system. Okay, and it can go, if it is electric bus, whatever capacity of the motor, you can go up to that range. There is no problem. Suppose if the 50 kilo, yes, that can be done. So this configuration, this integrated facility has a many features. One is the fast charging, and it will be as high as the level 3 charger. Okay. So same thing I said, if you connect the first two vehicle VSC1, VSC2, so it will act as a DC to AC to DC conversion, and both will provide DC power, and it is connected here. This rear side two vehicles, they can be connected, and it can feed power to charge this battery. So this way, this is called the multi-phase DC to DC converter. So in this one more attempt was done. This is some photographs of our setup. Same thing which was there earlier. Same configuration, single phase AC to DC converter, PFC converter, AC to DC conversion. This is the earlier we tested independently. We got 120 volt. See, before PFC it was 72 volt, and now somewhere I press the gate driver circuit. See here, current waveform is not sinusoidal. It is now we are turning on. Somewhere here the press it is turned on. Now current start becoming sinusoidal. So this shows now the here power quality issue is maintained, 5%, less than 5% THD. Current and voltage almost sinusoidal. See here, top two waveforms. Here individual current waveform of the winding, motor winding is given. And then when both are added, pink color waveform is the source current waveform. This is the 108 volt DC you are getting, and that DC is acting as an input for the multi-phase DC. So that topology is the separate one. Again same configuration. That was around 23. It is not visible to me, but it is 19. It is the latest bit. In 2023 it was captured. So same way, if the performance under steady state, THD is 2.9. This is the voltage THD. Current is 4.9 ampere current is driving, and current is 3.8% THD. So one small attempt was made to do this task, but again some problem arises. Yes, here. Also some typical situation. here one attempt was made. Since in multi-phase DC to DC converter, DC side, there was a 6 inductor or 3 inductor. And when you are going to operate this converter in closed loop control, you required sensor. So at least you required 3 sensors for sensing 3 individual current. If it is a 6-phase machine, then you required 6 sensors in each winding of the machine to sense the current. So there is a possibility, why not we sense one current and we can calculate rest of the winding current. So that was done, attempt was made here to do the same task. Like each winding, so here the role was to make the sensor reduction. So if topology comes, I will, like this, see, here you required 6 sensors to sense each winding current. This is the conventional. But if I place this sensor somewhere here, like here, you need not to sense individual current, you sense only one current. Each sensor current costing around 1500 rupees. If you add the PCB design and all, it comes around 200. So here if you add it, it will be 6 times up to around 18,000 or 20,000 you can spend on that. But if you replace, you can get, if you put current here, you can reduce the sensor requirement. So in this what I did, I had to put sensor here, and if you see the operation, when the one switch is on, current will flow from here. When the 2 switch is on simultaneously, then sum of 2 current will flow from here. That way, pattern of current is now recognized. And that current is further edited, manipulated, and we got the actual current. So in rough sketch, you can understand, I have one sensor to reduce the sensor requirement, do the estimate is all the 6 current. So that was done in this, and it was already communicated, but it is not yet published. So that part is there, and it is under review in IEEE transaction on power electronics. Okay. So the same thing it was done. For example, here it was done, if the duty ratio is less, then current, DC link current is like this. DC link current means this current. Okay. So this pattern will be there. If this pattern will be there, then I1, I2, these 6 are the some sampled current. Again, if you see the pattern, this current and the switching waveform, normally how the pulses are generated, again I think it is more specific, but you see there is a carrier wave and there is a control wave. So if you have a triangular wave and you compare with the carrier wave, then the pulses are generated. Okay. And like here we have a carrier wave, and if you compare, then the pulses are generated. Each pulse is, let's say the A phase. So when this phase is rising, here there is a pattern. In one particular case, red is rising and other are falling. See the identity in this 6 current waveform, jo hona chahiye, that is the actual. So one is red color is rising and rest are falling. Or in one case, let's say that this green was rising, others are falling. So if the duty ratio falls within this range, then one gate, and this is rising means that switch is, corresponding switch is on, inductor receives positive voltage, current is rising. So that was, means this waveform related with this carrier wave based on the duty ratio, and then we are estimating the average current. So that was the entire story, that was dedicated part. But here we can do the estimation. Like those who are doing research in the drive area, they measure the DC link voltage, and based on the VSC voltage source, VSC switching, they are calculating the phase voltage of each inverter. So that same way we did, we measure the DC current and we are estimating the individual current. Idea is to reduce the requirement of the sensor. So that if the 2 phase, suppose duty ratio falls within this range, on time is increasing, then this kind of pattern will come. Then this is the relation, and then you have to manipulate this to find IA, IB, IC, like all the current. So that whole structure was done. This is the control. We are sensing this, then duty ratio we are identifying, and then these are the current. That all calculation was done. And finally, the result was obtained. So we have seen the actual current, like this is the actual current, and the green color is the average current. This yellow color is the actual current, and RE restructured, means calculated, is the average value. So if you calculate the average value of LO, it will fall near to this estimated current. So that was done, and it was recorded during, I think, May 20, 2023, almost 7 months before. So it was working, and so that attempt we have made, and it was more specific, more local to power electronics people. They can more appreciate. But what the theme is, technology is there, concept is there, theory is there. Only thing, you have to explore it, and you have to zeal to implement it. You have to sit with your student, or either at any level. The invention can be done from the bottom to top. There is no restrictions, only the IITians will do. Everybody can do. Okay? So, there is a single book, same book we are studying, like for machine, the book which you have, same book we are reading. Only maybe the teacher may be the different, exposure may be the different, but you have to continuously be in touch with your student, with your books, and the dialects should be established related to the related topic. If you are sitting in the office discussing something different than the actual, then nothing will come out. So, whenever sit with your student, at least for that time you talk with your concept. Encourage them to participate in healthy discussion rather than off-track discussion. Okay? So, same, one more attempt was made from the DC side, because multi-phase DC to DC converter we saw. So that was now removed, and we have made some more things to do here. That what is the time to finish? Time is.
Yes, sir.
ऐसा तो नहीं पहले हो गया?
नहीं sir, we are running out of time.
Okay, no problem. So this is all from my side. I'll be happy if I receive comment for improvement so that we can improve further. So thank you everybody.